Hello students, good day. I hope all of you are well. In the previous lecture, we got introduced with the concept of deadlock and various terminologies. Today, moving on to the same concept, we will discuss multiple characteristics that are associated with the deadlocks as well as multiple methods to handle deadlocks. Deadlock in general is a state of the system when we have multiple processes present in the system and they are ready to get executed. However, because the resources that are required by these processes are already occupied by other processes, so processes are in indefinite wait and the system doesn't perform any useful task. So we call such state as the deadlock. You can consider its example as a system having two drives. If at any given time there are two processes running in this system and require both of these drives to complete their execution. So if at any point in time process 1 is holding drive 1 and waiting for drive 2 while process 2 is holding drive 2 and waiting for drive 1. So in this case, both of these processes, they are holding one drive and at the same time they are waiting for the drive that is already being held by the other process. So in this way, both of these processes will keep on waiting for the resources already occupied by the other process. And that is how you will see no useful work being done in such system. So in a deadlock, we have multiple processes which are blocked because their desired or required resources are already occupied by other processes, and in turn, those processes are also waiting for the resources that are acquired by other processes. Over here we have an example of a deadlock in the form of a bridge crossing. So you can see that on this bridge we have a shared resource where only one vehicle can drive at any given time. So this resource is the bridge and these vehicles are the processes. So if there is a deadlock, which means that each of these processes, they are waiting for the other processes to release some resource that is required by the first process to complete its execution, then we may have a deadlock in this system. And you probably can intuitively think that in order to resolve this situation, you may require some processes to back up from their original position, and which means that in a system having such situation, you may require to forcefully take back resources already given to a process to break this cycle. However, when we have such solutions, there is always a possibility of starvation. That if you forcefully take out resources from processes, there is a possibility that a particular process may have to uh, starve every time. There are several characteristics of deadlocks that are important to understand the whole concept. And these characteristics are important also because they can help us to deepen our understanding about the concept, as well as we can utilize them to find out methods that can be used to resolve or handle deadlocks. Over here we have four conditions that, if held simultaneously, will lead the system to a deadlock. These conditions include mutual exclusion, hold and wait, non-preemption, and circular wait. Now we will discuss each of these conditions in detail to have a richer understanding of this concept. The first one is mutual exclusion. This characteristic is associated with the type of the resource. There are several resources that can be shared in a joint manner, while there are other resources that can be shared in a several manner. For instance, if you have a processor, at any given time, only one process can hold that processor. Now, which means that this resource is taken in a mutual exclusion inclusive fashion. The same is true for printers. At any given time, the printer can only print one document. However, there are other types of resources which can be shared in a several manner. For example, your RAM. So in such resources, multiple processes can share those resources without affecting each other. So mutual exclusive resources are responsible for deadlocks because at any given time only one process can use that particular resource, which can lead to a deadlock. So to have a deadlock in the system, it is important or necessary to have some resource that is mutually exclusively occupied by a process. The second condition is hold and wait. Once we have resource which is of mutual exclusive type, the second condition is that if a process is holding that resource and requesting for another resource which is again of mutual exclusive type, then we have the second condition of deadlock. Again, having both of these conditions is necessary to have a deadlock in the system. So first of all, resources should be of mutual exclusive in nature, and then processes are holding them in a way that one process is holding one resource and it's requesting for the other resource. So holding a resource and waiting for the other one is the second condition that lead us towards a deadlock. The third condition is non-preemption. In systems, when we are unable to forcefully withdraw resources from a process, this is also a condition that is necessary for a deadlock to occur. Because if we can take back the resources forcefully, we can break the cycle at any point. So if in a system setting we do not have this privilege to forcefully take back the resources from a process, this may also lead towards a situation where we may have a deadlock in the system. The fourth condition is circular wait. Now, once we have mutual exclusive resources and we have processes who are holding some resource and requesting for the other resource, in the system we do not have this privilege to forcefully take back the resources. So the last condition is that this wait is in circular fashion, which means that if process 1 is holding the first resource and waiting for the second resource, while resource second is being allocated to process 2, which is again waiting for another resource, and eventually this makes a cycle that leads back to process 1 and resource 1, then the whole system will be in a deadlock. Once we have all these four conditions parallel in a system, we will say that the system is in the deadlock. If all of these four conditions hold simultaneously in a system, the system will be in a deadlock. In order to remove that deadlock, we have to modify one of the conditions. Also, it is important, if just one of these conditions is not present in the system, then there will be no deadlock. So having this understanding will help us how we can solve this situation of deadlock. All right. So after having an understanding about the four necessary conditions that are important or necessary to create a deadlock in a system, let's discuss some methods that can be used to handle a situation where we have deadlocks. There are three broader methods to handle deadlocks. The first one is we may ensure that the system will never enter into a deadlock state. The second, that we let the system enter into a deadlock and then we recover from it. And the third method, that we ignore the problem of deadlock altogether and pretend that deadlock may never happen in a system. The third one seems the most naive method to deal with the deadlock, is often the one that is used in most of the operating systems. The reason behind this selection is that the prevention mechanisms and the avoidance mechanism, they may require more resources to run a system in a smooth fashion. So if we just ignore the problem and let the system enter into a deadlock, this particular situation may occur only once in a while, and still the cost of this may not be as much compared to the methods that we install or implement in order to prevent the deadlock altogether. Moving on, under the first two broader methods, we have some categories which can be used to deal with the deadlocks. In the first method, where we ensure that the system will never enter into a deadlock state, include prevention and avoidance of deadlock. Prevention means that all the four conditions that we discussed earlier that are necessary to for a deadlock to occur in a system, we ensure that at least one of those conditions it never holds in a system. So we prevent the deadlock altogether. In the avoidance, we ensure that the system remains in the safe state. We will discuss what is the safe state in a while, but it means that there is not a possibility with respect to the resources that the system may enter into a deadlock. The second method, where we let the system enter into a deadlock and then we recover from it, we have some recovery methods to solve or to deal with this problem. In the first broader method, where we ensure that the system will never enter into a deadlock state, the first technique is prevention. In prevention, we prevent the system to enter into a deadlock state by ensuring that at least one of the necessary conditions for the deadlock may not hold in a system. So let's discuss those conditions along with the measures that we take to prevent the system entering into a deadlock. The first condition is mutual exclusion. So if the type of the resource is shareable, then we do not require any method to deal with it. It can be shared without any trouble. However, if resources are required to be shared in mutual exclusive fashion, we actually can't help to solve this situation. The second condition is hold and wait. In this condition, a process is holding a resource and waiting for another resource. So to solve it, we may have several solutions. One possibility can be that towards the beginning of a process execution, it may request all the resources that it may require. So we allocate all the resources to a process before it starts its execution, and it will release all the resources once it completes its execution. This solution may seem intuitive, however, it leads to low resource utilization, and because a process may hold multiple resources simultaneously in a system, it may lead to starvation as well. The third necessary condition for a deadlock to occur is non-preemption. So to prevent this condition to occur, what we can do is that if a process already holding some resources and request another resource which cannot be allocated to it at the moment, we forcefully take back all the resources that are already being held by this process. So if a process is having multiple resources and it requests for another one, and you see that this resource cannot be allocated to this process immediately, then we take back all the resources that are already being held by this process. And all the resources that we just took from this process, we add them to the list of the resources that are required by this process to complete its execution. So in this way, a process will only start its execution again once all the resources, including the old one as well as the new one, are free, and we can allocate all of those resources to this process immediately. So in this way, the third condition of non-preemption can be achieved. The fourth necessary condition is circular wait, where multiple processes present in a system form a cycle of request and allocations. To prevent this, we can form a total ordering of resources that are present in the system. This total ordering form a hierarchy of resources where two resources may not be at the same level. This hierarchy, which is one way, prevents the processes to request the resources in the opposite direction. So it prevents the whole system to form a cycle among multiple processes that are present in the system at any given time. The second technique to ensure that a deadlock will never occur in a system is avoidance. In avoidance, we ensure that the system will always remain in the safe state. By safe state, we mean that there is no possibility of a deadlock in the system. However, to achieve this safe state, the system may require more information from the process before they begin their execution. One of the ways to get this information is asking the process to declare the maximum number of resources that it may require during its execution. So the system dynamically examines all the resources in the system and the allocation state of each process to ensure that there is no circular wait in a system at any point in time. The state of resource allocation is computed by having the number of available resources as well as the allocated resources and the maximum request possible by each of the processes. So formally, when we say that a system is in the safe state, we say that having a, a particular number of resources present in a system, any process may not be able to lead the system in the deadlock state. So usually it is defined that if we have n number of resources and if we have j processes, all of those processes, they can complete their execution within the n resources that are present in the system at any point in time. So this means that it is possible that all the resources that are required by a process P1 may not be available at the moment. However, when P2 may complete its execution and return some resources to the system, P1 may get all the resources and it can also complete its execution. In this way, if we have j number of processes in the system, all of them may have a safe exit, or there is a sequence which is possible under the available resources that all of them can complete their execution within the available set of resources that are present in the system at any given time. This is how we visualize the safe state. So if the system is in the safe state, there is no possibility of a deadlock. However, if the system is in the unsafe state, still it is not confirmed that there will be a deadlock state in the system. However, there is a possibility of a deadlock when the system is in the unsafe state. So to wrap up, if the system is in the safe state, we will say that there is no deadlock possible in the system. However, if the system is in the unsafe state, then we have a possibility of deadlock. An avoidance mechanism means that we ensure that the system will never enter into an unsafe state. Various methods that are used to compute the safe state of a system also requires an introduction to instances of resource type. Instances means that how many copies of a particular resource is present in a system. For instance, if you have two printers, it means that there are two instances of the printer resource present in a system. So if we have a single instance of each resource type, then we can use a resource allocation graph for ensuring the avoidance in a system. However, if we have multiple instances of some resource types in the system, then this resource allocation graph may not work efficiently. To solve this problem, we may require to use the banker's algorithm. So this discussion of single and multiple instances of resource types will get clear when we will start the resource allocation graph discussion. So over here we have resource allocation graph, which is used to identify whether the system is in the safe state or not. However, we just discussed that this resource allocation graph is useful only when we have a single instance of each resource present in the system. Alright, so just start discussing this the resource allocation graph. In this algorithm, we usually reflect our processes and resources through vertices and edges. In such systems, we have two types of vertices. First is P, which is processes, the number of processes that are present in a system, and the other one is R, which is the set of resources that are present in the system. So the resource allocation graph is a graph that comprises of some vertices and some edges. The vertices can be of two types. Either they can be processes or they can be resources. And then there are also two types of edges. The first one is a request edge. If we have an edge from a process to a resource, it means that this process is requesting this resource. So it's a request edge. The second type of edge in this graph is an assignment edge. If we have an edge from the resource to the process, then this edge is termed as assignment edge. So now we have a graph where we have some vertices and some edges. Vertices are divided into two types, processes and resources. Also, edges are of two types. One is request edge, where we have an edge, a directed edge from a process to a resource. And the other one is an assignment edge, which goes from a resource to a process. So request edge means that the process is requesting for a resource. And assignment edge means that this resource is already being allocated to this process. Over here, we have a visual representation of all of these four constructs. So the first type of vertex is a process, which is represented by a circle. The second type of vertex is resource, which is represented by a rectangle. You can see that over here these dots reflect that how many instances we have of this resource type in a system. So for this, having this rectangle with these 4 dots, we have 4 instances of this resource type. So here we have the first type of edge that moves from a process to a resource, and it is a request edge. And over here we have an assignment edge where this edge moves from a resource to a process. Over here we have an example of resource allocation graph. Let me read it for you. So in this graph we have 4 resources, R1, R2, R3 and R4. R1 and R3 have 1 instance each, while R2 has 2 instances, while there are 3 instances of resource type R4 in this system. Over here we have 3 processes running in this system, P1, P2 and P3. At this particular point in time, P1 is holding R2 and requesting for R1. P2 is holding R1 and R2 while requesting for R3. P3 is only holding R3 and requesting for none. So this is how we may read this graph. Now assume if process P3 requests for R2. Now we have a deadlock in the system because P3 is requesting for a resource that is already being held by 2 other processes, P1 and P2, and the resources that are requested by P1 and P2, they are already occupied by P2 and P3 respectively. So there are 2 cycles in this system at this moment. The first one is R2, P2, R3, P3 and R2. So this is the first cycle, and the second cycle is R2, P1, R1, P2, R3, P3 and R2. So in the presence of both of these cycles, there is a deadlock in the system. Over here we have another example of resource allocation graph with a cycle. The cycle here comprises of R2, P1, R1, P3 and R2. However, as some of you may have already observed that there is no deadlock in the system because R2 has another instance that is being allocated to P4. So once P4 may complete its execution, this R2 can be allocated to P3. In the same manner, as P2 has already 1 instance of R1, once P2 completes its execution, P1 can get this resource and then again there won't be any cycle in the system. There are some insights that can be inferred from the above discussion. So if the system has resources with single instance and if there is no cycle in the resource allocation graph, we can assume that there is no deadlock in the system. However, if there is a cycle, we will have a deadlock. On the other hand, if we have resources in the system that have multiple instances, then no cycle means that there is no deadlock in the system. However, this time, even if we have a cycle in the resource allocation graph, still we cannot be sure about the existence of deadlock. So there is a possibility that we have a deadlock, and we also have a possibility that there is no deadlock in the system. So for this reason, this resource allocation graph is a lot better suited for single instance of resources. Now let's try to identify a scheme through resource allocation graph through which we can decide the existence of a deadlock in a system. So we are already familiar with two types of edges. The first one is a request edge that goes from a process to a resource, and it means that a process has requested a resource. The second type of edge is an assignment edge that goes from a resource to a process, and it reflects that a resource is already allocated to the process. However, to make sure that we are verifying the existence of a deadlock, this time we are also having another type of edge, that is a claim edge. This claim edge goes from a process to a resource, and it determines that a process throughout its lifetime may request a particular resource. So this is not a request in real time, but this is just a possibility that may occur throughout the lifetime of this process. So now this time we are evaluating claim edges along with request and assignment edges to make sure that we are not converting any request edge to an assignment edge if there is already a claim edge. By this we mean that we are not allocating a resource to a process if there is a potential request by a process that is not yet being requested. Now let's try to understand this through an example. So over here we have two processes and two resources. Assume that P2 process has requested R1 resource, which is already allocated to P1. So this P2 requests R2. Although this R2 is free at the moment, there is a potential request from P1 that may execute throughout the life cycle of this P1. So although this R2 is free, we cannot allocate it to P2, because if we allocate it to P2, there is a possibility of a cycle by this particular edge from P1 to R2, and if it executes, then there will be a cycle in the resource allocation graph. Over here we have that modified diagram where you can see that by converting this request edge into an assignment edge, we have a potential cycle in this system. So we will straight away avoid it. So the algorithm of utilizing resource allocation graph for the avoidance of deadlock is quite straightforward. A request will only be granted if by converting a request edge to an assignment edge doesn't create a cycle in the system or the possibility of a cycle in the system. So a resource is only allocated to a process if there is no potential request that makes a cycle in the whole system. To wrap up this whole discussion, if the resource allocation graph has no cycle, it reflects that there is no deadlock in the system, no matter whether we have single instance or multiple instances of resources. However, if the resource allocation graph has a cycle, then we have two possibilities. If we have single instance of resources, then we have a deadlock in the system. However, if we have multiple instances of resources, then there is still a possibility of deadlock, but we cannot say with certainty that there is a deadlock in the system. So this resource allocation graph can be efficiently used when we have single instance of a resource type. For multiple instances, we have to use some other method. Usually we use the banker's algorithm. We will discuss this banker's algorithm in the next lecture. For today, this is all. Thank you, students.